We'll set up our table of values. In our independent variable column heading, we'll have the number of socks produced, S. In our dependent variable heading, we'll have the cost of the shipment, C. This is determined by C is equal to 20 plus 2 times S. For 10 socks, it's 20 plus 2 times 10, or $40. For 20 socks, it's $60. For 30 socks, it's $80. For 40 socks, it's $100. And for 50 socks, it's $120. Again, considering the same example. Miranda has been asked to display her information in the form of a graph, since this is usually the best way to display statistics, especially for those who aren't good at reading raw data. Her investors are really interested in knowing how their money is spent. To change this into a graph, we need to create a graph with a scale and some labeled axes. Recall that the dependent variable is cost. That always goes on the vertical or y-axis. And the independent variable is socks produced, which always goes on the x or horizontal axes. We've chosen an appropriate scale and will now just plot the points. 10 socks, $40. 20 socks, $60. And so on and so forth until the points are all plotted. Then we can connect them with a straight line. This line represents the growing cost of producing socks. So we have our line. Remember, the y-intercept is the point where the graph crosses the y-axis. In our situation, the y-intercept is 20, represented by the point 0, 20, or b is equal to 20. What is significant about the y-intercept? Well, this 20 matches up with the initial value, and it matches up with the constant that's added in the equation. Remember, the slope is the steepness of the line, as calculated by m is equal to rise over run. What is the slope of this line? Well, if we calculate the rise and the run, we'll see that we have a rise of 100 and a run of 50. Putting these into the formula, we'll find that m is equal to 100 over 50, or 2. Have you seen this number before? That's right. This 2 is the $2 to produce each sock. That's the rate of change. And you can see it in the formula in front of the independent variable. Again, dealing with socks. What happens to the table of values if you move the line up or down? This is an interesting idea. If we move the line up, we haven't changed the rate of change, or the cost to produce each sock. We have, however, increased the initial value. That's the shipping cost. So each of the values would then go up. Since the initial value was 20 and it's now 80, they would all go up by 80. If we brought it up even higher, they would all go up by 100. And if we brought the shipping cost down to 0, we would notice a change in the equation where c is equal to 0 plus 2s, and all of the values would go down significantly. However, the spacing between them, the rise over run, or the rate of change, does not change. The initial value, the shipping cost, changes, but the rise over run does not, which leaves us with parallel lines. Recall that our original was here, and our other values were here, here, and here. And as I mentioned, the slope, or the cost to produce each sock, remains the same. What happens if you rotate the line? So if we make the line steeper. If we make the line steeper, the initial value, or the shipping cost, remains the same, but the slope, or the cost to produce each sock, changes. In this situation, our slope has changed, and you can tell that by a rise over run, a rise of 120 and a run of 40, which leaves us with a cost to produce each sock, or a slope, or a rate of change, of $3. This would affect our table of values by changing our equation. Instead of C is equal to 20 plus 2s, we would have C is equal to 20 plus 3s, and each value would change accordingly. If we were to rotate the line even steeper, the initial value remains the same. However, the slope, or the cost to produce each sock, again would change. In this situation, the rise in the run would now be 120 and a run of 20. So that would mean the cost to produce each sock would be $6. You can see this change in the table of values. Notice how the values are further spaced apart. And if we rotate the line to be less steep, we would see, again, the initial value, or the shipping cost, remains the same, but the slope changes. Now we would have a different rise and a different run. If we had a rise of 40 and a run of 80, we would find a slope, or a rate of change, or a cost to produce each sock, of 1/2. This would change our equation and all of our values. Notice how the values become closer. Example: Sean's car rental company charges $35 plus 25 cents per kilometer driven. What is the equation that would model this situation? Come up with an equation and come back to check your result.